Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, folks, let's go ahead and get started. Today we have Winter Mason here from Yahoo Research, and pleased to welcome and introduce Winter. Winter has a unique and potent background. He got his PhD at Indiana in a combination of cognitive science and social psychology. So he's adept at thinking about people in a very, very small, sort of down to the neuron level. And has spent the last year and a half or so at Yahoo Research, where he's thinking a much, much larger scale, so social network scale. And so he's one of the rare people who can think at sort of multiple levels of analysis with respect to social computing. And today he's going to talk about social networks and success. So please welcome Winter Mason.
Thanks for having me. Thanks, Scott, for introducing me. As you said, I'll be talking today about social networks and success, and I'm just going to open it up by asking, trying to answer why could social networks affect success, right? So one thing is that social networks affect the information, the access that people have to information. So people in different positions within a social network have access to different kinds of information, and they are able to broker information between other individuals that they are connected to. And as a result, you can see, a person might be more successful because they're in a better position with respect to the information that they have available to them. Similarly, in information diffusion, if you want to, reach a whole lot of people and you want to, affect a large number of people, then you might think about, information diffusion and how far and wide a person's influence can reach. And this, of course, will also be constrained by the social network that they're embedded in. Another way that you can think about it is with respect to work groups. So work groups, share information, they share resources. Resources are distributed amongst people, and this distribution, the way that these resources and this knowledge and the capabilities are distributed within the social network of a work group, can actually influence the way that the group as a whole can act and respond and behave generally. And so you can actually think about how the internal social networks affects the entire group's success. So what I'm going to do is I was going to talk about 3 projects, but I'm going to, I've pushed one to the back in case I don't have enough time. But basically I'm going to talk about a couple of research projects, one that I did in my PhD, and the other that I just did recently. So the first thing that I'm going to talk about is this project that I did with my colleague Sid Suri, where we're basically looking at social networks and success of individuals. Now, this has actually been addressed in the sociological literature under the rubric of social capital. Okay, and so social capital is meant to be analogous to human capital and real capital in that it is actually resources that you can draw upon. And so out of the numerous definitions that we saw in the literature, we felt like this one was the most representative of the way that people have been thinking about social capital. And we only tweaked it a little bit. This is Nan Lin, who we're citing here. And the definition is social capital can be defined as resources embedded in a social structure, which could be accessed and or mobilized in purposive actions. Okay, so the two key parts of this definition is the social capital is actually embedded in the relationships. Okay, so a classic example of social capital is simple reciprocity. Okay, so I do a favor for you. Now you are a resource that I can draw upon because we have a relationship of established reciprocity where I know you owe me a favor and you're going to do me this favor because I've done you one. Right, and this means that I can, access these resources and maybe even get you to do things, act in a particular way by utilizing our relationships. Okay, but this can, what crucially is that it's not just reciprocal relationships that are important. You can have entire networks. And so the literature on social networks, on social capital has tended to focus on two particular aspects. The first, two particular sources of social capital. The first is network closure, and this is, or cohesion, and this is the position that's been advanced by Coleman. And basically the idea here is that if you have a very cohesive network surrounding you, the people that you're connected to are very strong ties, you're going to have a lot of social support. So if you run into any problems, they'll be there to help you out. You get into debt, your family can bail you out. Later on, you get a job and you can pay them back, right? So if you have a community that supports you, then that can actually kind of buffer your losses and therefore improve your overall success, right? You also, if you have a tightly knit network, you might have this network of reciprocity and trust. So you can say, well, I did a favor for John, and John did a favor for you, so now you need to do a favor for me, right? So if you have this kind of nice community and tight-knit network, then this can actually improve the resources that you have available to you. Finally, a lot of these tight-knit networks, in this argument, a lot of these tight-knit networks are based in some community, right? Some real, a lot of these studies have focused on ethnic communities where they're looking at, how these social norms are established that enable people to kind of, it's not just the trust, but it's also kinds of the understanding of behavior and how you're going to react to certain things. And so if you have this tight-knit community, then, you can enforce these norms, you can sanction these norms, you have this very, developed, whole community trust. And so there's this whole theme of literature based around saying that individuals can be more successful if they're embedded in a network that is very cohesive and very strong. However, there's also this competing view which says that if you're in a position that bridges different communities, okay, so rather than being tightly embedded within a community, if you're actually bridging different ones, then that's going to be better for your success. So one reason this might be is something that I alluded to just moments ago, which is that you have access to a wider range of information. So if you have different communities that are all very homogeneous in their ideas, they're all sharing the same norms, they're all sharing the same information, and you have access to multiple communities, then you can draw from all of this, combine it, and put it together. You can broker the relationships between the groups, as I mentioned. So if you're a single seller in a network of buyers, right, you can play the buyers off of each other, assuming that they're not connected, to get the lowest price possible. Of course, if you're not in this bridging position and the buyers are actually communicating with each other and colluding, then you don't have this option, right? So if you're in a position where you can broker, then this might be good for your social capital and for your success more generally. However, so Sid and I were looking at this literature and we felt like there was some kind of glaring missing things. The first is, there's other sources of social capital. You can imagine other sources of social capital other than just, being in a tight-knit community or bridging different communities, right? Like maybe an important thing is simply having a whole lot of resources and people to draw from, right? Maybe if you are, Ashton Kutcher and you have 1 million followers on Twitter, that actually is a better resource that you can draw upon than, if you're, than if you only have a few friends, right? Another thing is maybe actually just centrality in the network as a whole. So maybe it's not just important that you're bridging different communities. Maybe if you're at the center and information has to flow through you for the whole network, that's going to be the thing that's most important. And in fact, there's probably many other sources of social capital that you can imagine that would generally benefit an individual. Moreover, for any given source of social capital, there's likely to be multiple measures for that source, right? So for the sociologists that have been studying bridging and advocating the bridging perspective as this is what's important in terms of network position for success, they tend to focus on a single measure that Ron Burt came up with called network constraint, where the idea is that if your social network is highly constrained, then you don't have a lot of structural holes and therefore you don't have access to resources. But of course there might be many different measures of bridging, or there might be many different measures of cohesion. And so we just felt like this was kind of missing. Why not look at all of these things and more? And even on top of that, what about the possibility that being in a network position where you kind of have a strong network around you, but you also have weak ties to other things. Maybe that's even better than being in a position that's simply bridging or simply in a tight-knit community in and of itself. So what we did is we said, okay, we're going to take advantage of the fact that we have lots of data. We're going to get lots of data, and we're going to look at different measures of success. So what we did is we looked at these 4 different data sets. So CiteSeer and CiteSeerX are both co-authorship networks. They're both data sets about publications and citations. CiteSeer is actually somewhat of a subset of CiteSeerX. Basically, CiteSeerX was a subsequent crawl of the web. Both of them were designed at UPenn to Penn State. Thank you, to crawl the different citations. And so basically, what we did is we just took the projection of the bipartite network between authors and papers and said 2 authors have a tie if they co-authored a paper together. Our measure of success in these 2 data sets is the number of citations received, just the raw count. Now, of course, this is not perfect, and there's a lot of things about you can use, eigenvectors or eigencentrality on the citation graph to figure out the, best impact. There are a bunch of different ways of measuring success, but certainly the raw number of citations is a reasonable measure of success in an academic community. So what we were interested in for these 2 was basically, does a person's position within their co-authorship network affect the number of citations that they receive, and also the number of citations per publication that they receive, so their average kind of success of their papers. For LiveJournal, what we did is this is similar, it's very comparable to the co-authorship networks, except now we're looking at blogs. And so we have 2.2 million bloggers, 400 million blog posts, and the social network that we're looking at is this explicit friend network where people actually say, I'm a friend of this other blogger. And our measure of success is comments, and we feel like this is it's a proxy for their readership. Okay, so if they have a lot of readers, they're going to have a lot of comments. And we also looked at the comments per post. Now, our last data set is very different, and basically the reason why we used it was because we wanted to look at a data set that had been analyzed from this traditional social capital perspective. Okay, and so Ron Burt has this paper where he analyzed this network of the Bureau of Labor Standards classifies all businesses into various industries, and then every 5 years they release a report that is the buying and selling between the different industries. Okay, and so you can construct a graph out of this buying and selling network. There's particular techniques that Burt did that we imitated, like cutting it off at the 2% line, so you are eliminating the weakest ties, et cetera, et cetera. But basically, so that's our buying and selling network, and then our measure of success is this thing called the price cost margin, which just to a rough approximation is like the profit margin for the industry. Okay. So what we did is we had a huge set of features that we looked at. We could have even done more. We just kind of did the ones that were computable and took a wide range as possible, used ones that were used in the literature, and ones that lined up with kinds of the sources of social capital that I just talked about. So things like cohesion, where you've got like clustering coefficient, betweenness, centrality, so you have like closeness and betweenness. Reach, so you have 2-hop degree and degree, et cetera, et cetera. Now, we also had some nodal features, some non-network features that we looked at just to see how the network features stacked up against non-network features. So, not just looking at the social capital stuff, but also other things that might be indicative of success. And there's a couple of features in here that I want to talk about. Specifically, one is the industry concentration score. Obviously, that only applies to our final data set. Basically, what it is it's just the percentage of output within an industry that is accounted for by the top 4 most producing businesses within that industry. It's I don't know who came up with it, but it's supposed to be a proxy for how dominated it is, a particular industry is by the top industry. So if you look at like car manufacturing, there's obviously like 4 companies that tend to dominate the market more than the rest. Whereas with like sheet metal manufacturing, there's a whole lot of little businesses scattered across the U.S., and so the industry concentration score is very low for those. The second one is ego components. This one was actually independently and prior to us coming up with it, created by Stephen Borgatti. Basically what it is if you take an actor and their immediate ego network and then remove them, how many disconnected components remain. And so in this way, it's kind of like a measure of bridging, because if you don't have that node there, how many different pieces are they connected to? How many different communities are they connected to? So our first pass question was, okay, so we have all of these features, right? How do these relate to success? All of them, all of these down here are specifically network features, and therefore they're capturing things, the relationships, and therefore it's going to be indicative of social capital and different sources of social capital. So the first thing that we did is we just looked at essentially correlations of each of these things with the various measures of success. So in CiteSeer, we're looking at total citations. We looked at the sites per pub and the features and found that they had a very heavy-tailed distribution, and so we took the log to normalize the errors. So what we see here, just a couple of quick points. Basically, the very most predictive feature in both the average citations per publication and the total number of citations is the number of publications you do. So what this means is that if you are highly productive and you're outputting a lot of papers, that's going to be the more that you do that, the more citations you get, and the more citations per paper that you will get. The most predictive network feature is the maximum weight. Okay, so the weight is essentially the number of papers that you've co-authored with a person. Okay, so that's the weight on the edge. And so if you have one person that you've co-authored many, many papers with, that's also correlated with the number of citations that you will receive. The most predictive structural feature is 2-hop degree. And it's interesting, so more than just the number of co-authors you have, right? But the number of authors that are reachable within 2 hops of this co-authorship network is more predictive of the number of citations you receive than just the number of co-authors you have. Okay? So here's a situation where you're really getting at I feel like the most likely explanation for why this is true is because you're actually seeing information crossing. So if I'm connected to somebody that's co-authored with other people, and if the number of people that I've co-authored with reaches a wide range of people, that's actually more predictive of success, and that's actually going to influence my ability to get citations. Yeah.
Sorry, so your definition of success is just the total number of citations.
That's right.
Unnormalized by anything.
That's correct.
Well,
we also have sites per pub.
Yeah. Okay.
So yeah. And in fact, the ordering of these features in terms of their, how predictive they are of citations and citations per publication, tends to be pretty similar. Obviously there's some variation, but for instance, the maximum weight and the 2-hop degree are, up here, and then the maximum weight and 2-hop degree are up here. So certainly in terms of like the ultimate ordering of all of these things, you're seeing these particular features be predictive both of total citations and citations per publication. I will only talk. I had one other thing that I wanted to say on this one, which is that our measure ego components, which is probably the one of several various measures of bridging, actually in this domain is way more predictive than network constraint of the number of citations you receive. So the sociologists that have been using this network constraint as a measure of bridging, maybe at least in this domain, looking at other measures of bridging would be a better idea. I'm not going to talk too much about CiteSeerX because actually what we see is very similar to CiteSeer, which is not surprising. It's the same domain. There's even some overlap in the data, so it's not too surprising. But basically, number of publications is first, maximum weight is the most predictive network feature, and then 2-hop degree is also very predictive. So it's very similar to CiteSeer. What's interesting is that when we look at LiveJournal, we actually see a similar order of the variables again, right? So the one difference being that degree is much more predictive of the number of comments the total number of comments you've received than the number of posts you have. Not a whole lot more, but more. And we think that there's some reasonable explanation for this, right? Like, so the reason that you're creating an explicit friendship to somebody in this blogging network is because they're somebody that you're interested in reading their blog. And if you're interested in reading their blog, then you're likely to comment on them. And so if you have a large degree, you have a lot of people that are potential readers of your blog and therefore likely to comment on it. But again, we're seeing, it's not just the immediate people that you're connected to, it's 2 hops away that's being important. And incidentally, we thought about, okay, well, we could do 3-hop degree, but it just turned out to be computationally intractable, at least for the timescales that we were looking at. But again, also, ego components ends up being a very predictive feature, right? So yet again, and more predictive than network constraints. So here we've moved to a completely different domain outside of co-authorship, where now the edges we're looking at is this explicit friendship, and the measure of success is now comments, and we're still seeing a kind of similar ordering, okay? So we've gone through like 3 data sets, and we're feeling, okay, we're starting to see a trend here. We definitely feel like we're getting an idea for how things work and how these variables are related, at least on a first pass, just correlational nature with our measures of success. So great, it's telling this nice coherent story. Well, then we get here. And all of basically the orderings that we had seen, the relationships with success are all completely different here. What we're seeing is the industry concentration score is, relatively correlated. It's 27% correlation. I mean, it's not great. Concentration weighted NC. So what this is you take your network constraint measure and you weight it by the concentration score of the industries that you're connected to. This is actually, so these 2, industry concentration and concentration weighted network constraint, are basically the only variables that Bert used in this paper that we were comparing our results to. And what's interesting is that, so this is something that Scott and I were actually just talking about. So over here, the most predictive features, in LiveJournal and CiteSeer, the most predictive features are tending to be correlated between, 0.5 to 0.6, maybe even 0.7, right? So you're seeing these like very large correlations. And then over here in the industry data set, you're seeing these very, very small things. And, Bert has this long paper about how, talking specifically about this and how network constraint is very predictive of success, right? And how it's this clear measure of social capital. But then you look at his R-squares and they're like 0.2 at best, right? So, it's questionable. And so what we did, okay, so now we have this kind of very simple first pass understanding of how these features relate to success, right? So we can say some things at this point, right? We can say that there is a relationship between these network features and success. Okay, there is a positive relationship, a measurable relationship, a significantly different from 0 relationship with these network measures and success. We also can say that at least for some of our data sets, we saw this consistent pattern of the productivity being the kind of most predictive thing, measures of reach like 2-hop degree being the next most predictive. Before that, the strongest tie being most predictive, and then measures of reach. We see, bridging also being important. So we start to see these kinds of relationships. But of course, the question might be, there might be a confluence of different network features that are important for predicting success. And so, what we wanted to do is look at sets of features. But of course, before you do that, you want to look at the interrelationships. Now, I'm going to go through these. They're pretty pictures, but they're not that informative. There's just a couple of things that I want to share about them, which is basically, if it were true that there were only these 2 sources of social capital, the bridging and the cohesion, then you might expect to see kind of 2 groups of features kind of just falling apart, whether they are a bridging measure or a cohesion measure. But you don't really see that. And so basically the only thing that you really need to take away from these is that you do have these features that are highly redundant. Okay, these are intercorrelations where the more red it is, the more positively correlated they are. The more blue it is, the more negatively correlated they are. And I know you can't read any of these. Basically, suffice it to say, clustering is negatively related with ego components, which is completely unsurprising. It's positively related to network constraint, also unsurprising. So the kinds of relationships are not very surprising or particularly important. Just the key thing to take away from these is that there are these strong correlations that we have to take into account. Okay, in order to do that, what we did is we adopted a technique from the biostatistical literature, okay, which is this fast correlation-based filter. Because what we wanted to do, we didn't want to just, of course we can throw all of these features into a single, regression model. We also did regression trees. Throw it, and the results were comparable, so I just report the regression results. But basically, you could throw all of them into the model, and then that would really be maximizing your predictive accuracy. But what you want is really some sort of interpretability, right? I mean, what you kind of want to be able to say are statements like, well, controlling for the features in our model, an extra friend, an extra person in my social network is going to lead to so many more citations, right? But you can't do that if you have collinearity of your variables, okay? Or you can do it, but you'd be, your confidence intervals on the statements you'd be making would be way off, right? So what you do here, what this algorithm does, it's really quite simple. It's basically like a forward stepwise regression where you put in the most predictive variable, but then you apply this filter where you eliminate any of the features that are too highly correlated with that feature that you have in your model, right? And then you look for the next, after you've eliminated those, you look for the next most predictive one, put it in your model, and then apply the same filter to say, okay, now what is too collinear with the model that I have already, and then eliminate those features. And so essentially you're ensuring that you're always adding the most predictive feature after eliminating the ones that are too collinear. And so that allows you to interpret the variables. Yeah.
So there's an interesting data question here so let's say that you did something like principal components analysis instead, right, which would be a blend of all your features, and you could quickly find, given the amount of overlap based on the correlation matrix, I'd guess like 3 or 4 features would probably capture a lot of what's going on there.
Yeah.
So the problem, like you said, may well be an interpretability, because you then could say, well, this is a blend of this, much of this, much of that. But at the same time, I guess the question I would ask in return to the social scientists would be that, like, well, they came up with these heuristic features, right? They're not golden. There's nothing sacred about them, right? And it may in fact be that it's much more effective to use blended features.
I completely agree. And in fact, I think that to some extent, when you look at kind of the real core of what they're doing when they're doing these sorts of analysis and trying to make these predictions, really actually what they want is just the whole model. They really just want to be able to predict success as best as they can, right? But then there's this big, when they're talking about it, they make very strong claims about the theoretical basis and why, they make nearly causal statements about, it's always correlational studies, but they make these nearly causal statements about why this feature is important, and they spin a story about why this feature is important, right? And so, we're as perhaps you can tell, we were kind of pitching this to the sociologists, and of course, in order for them to kind of buy it at all, we had to make sure that there was this interpretability. And I think that maybe if you're really interested in organizational things or whatever, you can imagine maybe trying to tweak these variables so that you're getting the most success or whatever. But
alternatively, what you could imagine doing if one wanted to publish in the social psychology sphere, you could do something like you could say, well, I'm going to use PCA and find what the optimal features are. Then I'm going to make justifiable features, make a whole bag of them, and see which ones correlate best with those ones that I know are actually optimal.
Yeah.
And they would be like, wow, you've invented something.
That's not a bad idea, actually. Maybe I'll try that approach.
And another sub-question actually, which is semi-related, which is that. So you look at the correlation coefficients of these features with the thing. One thing I wonder about is that in terms of actual predictive capability, there's also the possibility of saying that, well, I'm going to look at this person over, n months, maybe the first 2 months they're on our network, and then look, n months into the future and see if I can say something about how they might perform.
We actually did that.
You did? Okay.
Yeah. I'm not going to talk about it though. We were doing essentially basically. Given the number of your network position at now, can we predict the increase in the number of citations you can have? We did that. Yeah. I decided to cut it just for time. So, right. Okay. So what we're looking at are sets of features. Okay. And so we've applied this FCBF algorithm where we're getting these coherent sets of features, and so this is CiteSeer, total number of citations I'm going to focus on first. Basically, if you recall, just looking at the number of publications was correlated with number of citations at about 71%. So the R squared was was close, I think it was like 51 or around 50, 51. Oh no, it was 49, right? So the R squared was 0.49. So even with all of the network features, so this is if you take all of the network features and throw them all in the model and how well does this predict success, it still doesn't do as well as just solely the number of publications, okay? But at the same time, right, I mean, this is, when you have them all in there, they're accounting for about 41% of the variance, and so that's not terrible, right? Especially given that the kinds of R squareds that you're seeing in other work on this tends to be around 0.2. You know, that's actually pretty good. And in fact, when you just take these 5 network features and put them in the model, you still account for about 38.5% of the variance. And so what's nice is that, you know, we are, because of the FCBF algorithm, we're guaranteed that these are not too collinear with each other, so we can actually make the kind of statements where we say, if for every additional paper that you co-author with your strongest tie, with the person that you've co-authored with the most, controlling for these other variables, you're going to get on average about 5.5 additional citations. Okay. Similarly, for every additional person in your 2-hop network, right, so every additional person within 2 hops of you in your co-authorship network, on average, you're going to get about 1/5 of a citation, okay, controlling for these other variables. Now, with citations per publication, again, what I don't think I was entirely clear on this. What we're doing is we're just taking the network features and applying the FCBF algorithm to them. That's what I'm showing you here. We also did it to the case where we were throwing in all of the features we had available to us and then applying the FCBF algorithm. And so I kind of have the R squareds here, but I'm not going to specifically talk about the features that are selected in it. And so when you just take the network features and try to predict the number of citations per publication, you really don't do a good job. You get about 8% of the variance, which I'm just going to say is none. And so, you know, you can't really, I mean, interpreting these features is not a good idea, basically. So CiteCRX, I'm going to just flip back between these two, and you see that, you know, the features that are being selected for are essentially the same in CiteCR and CiteCRX. So again, this is not terribly surprising because you're looking at, you know, the same kind of data. Yeah.
So I fully understand the ego components, but I see that CiteCRX doesn't have the ego components and CiteCR does.
That's right. So basically, it's not a huge contribution to it, and in fact, if you look at the just single correlations, that's one of the small differences between CiteCR and CiteCRX is that ego components is not as predictive.
Have a handle on that.
Oh, so just think, I mean, at a very rough level, it's just a measure of bridging, right? It's like how many different communities you're connected to. So if you have a set of people over here that are co-authoring together, and a set of people over here that are co-authoring together, and a set of people over here, then your ego components would be 3. Right. Whereas if you have everybody that you co-author with also co-authors with each other, or if there's a path connecting all of the people that you co-author with, then your ego components would be 1.
Why is that different from clustering?
Because the key is that what you're looking at is the number of connected components. So
Once you remove yourself, so you take yourself out of the
right, you just look at your ego network, you take yourself out, and then it's the number of connected components. So it's the paths between them. Yeah. Okay, so CiteCR and CiteCRX, not much difference. This ego components goes away. Even the D prime, the effect size of each of these variables within the models is pretty comparable across them. And again, with just these, in this case, with just these 4 network features, you're still accounting for about 34.5% of the variance. And yet again, you can't do a very good job of predicting citations per publication. The R squareds are pretty low. So this is a bit of a slog, but I'm almost through it. So LiveJournal, honestly, we looked at this, and essentially all of the variance is being accounted for by degree. So that network feature does a very good job. Interestingly, you can predict comments per post a lot better than you can citations per publication. The R-squared here is about 31.5%. And we, again, think that this is because of the large effective degree. In an industry data set, I was talking about how, with R-squares, in this range, you can't really interpret anything. And so, again, that's kind of what we find. Basically, because we don't have the concentration scoring here. And so, honestly, the conclusion that we reached about this industry data set is that all of the results that were seen in the previous publication of this were due to this concentration score, and it just seemed as though it were the network features. I mean, I can't say that 100% conclusively, but at least in our explorations of the data, that's kind of what it seems like. So which is unfortunate because our whole point of using this data set at all was to make comparisons to the past. So I guess it's good in that maybe we're addressing issues in previous work, but it didn't really help in terms of us being able to predict something interesting about industries in the U.S. So we can make some kinds of statements about, looking across all of these domains and all of these measures, we can make some kinds of generalizations.
Wait, but that's fantastically important, isn't it? I mean, you just said seminal work from a couple years ago that everyone has hung their theory of how industries communicate with each other isn't. They were actually measuring the wrong thing.
Yeah. It depends on how much okay, the reason I glossed over it is because I don't think anybody here has hung their hat on that particular hook.
No one in this room.
Well, right, exactly.
But I mean, sort of when I was in the social network analysis field, there was a lot of hats hung on that hook.
Yeah.
A lot of consultants making a lot of money making that claim.
I think that I mean the thing is that it's if you look at the original work, I mean, like I said, you're seeing these R-squareds that are on the range of, at best, 0.2. And so you kind of have to call into question why people were interpreting it in this way in the first place, right? I mean, so honestly, you don't even need to have done our analysis to know that it wasn't that great to begin with. And it's just kind of, I don't know. I mean, this is actually one of the reasons that we got into it is because we were looking at this paper and we were like, this just doesn't seem to make sense, and so we tried to address it. But really, what we had hoped was that by throwing in these other features, by looking at these other network features, we were actually going to be able to say, oh, you know what? It's not network constraint that's important. It's not the industry concentration score that's important. It's X. And we weren't able to do that. And so just having a negative result, kind of a null result, is not as strong of a statement as being able to say, we have some really clear positive result. Okay, so going across these different data sets, we can make a couple of, summarizing statements. One is that in almost every single case, including the industry data set, it was a nodal feature, that outperformed the network feature. The only case that this wasn't true was degree in the LiveJournal data set, predicting the number of comments received. In almost every other case, this measure of productivity or the industry concentration score was the most predictive. However, importantly, this is something that we feel like is kind of obvious but overlooked in the literature, which is that you take combinations of sources, so bridging and cohesion and reach, and put them in a model, and it does better at predicting success than any single source of social capital alone. Whereas, the literature was all about, it's either X or Y, and in actuality, it's X, Y, and Z. Of the network features, almost always measures of reach. In terms of how many resources you have available to you, we're doing the best job of predicting success. In terms of addressing this literature about bridging, we found that our ego components measure almost always outperform network constraint. And so, it's at least worthwhile to consider different measures and different sources when you're looking at different domains. So, I feel like there's just been this kind of, whitewash of this is how you treat social capital. For everything. And in fact, what we clearly see here is that there's differences between different domains and data sets.
I
Yeah.
have one more question about this, and I'm curious if either you or the previous authors have done this analysis, because so far what you've shown is something where you have a continuous measure of success, like citation multiplication or like dollars of volume capital, whatever. And you're kind of regressing for that, and you're showing the correlation coefficients for that. So an alternative way to look at it would say that I'm going to set a threshold for success, which is that like if you have more than 100 citations or more than 10 citations, like the R factor or H factor, whatever it's called, and for businesses some capital amount or whatever. And then say, okay, now I'm going to use a classifier or any other means I can.
Right.
And I don't care what combination I end up with or what crazy thing, but I want to see how well I can actually do the task of saying 1 or 0 for these things.
So I can definitely tell you nobody has done that.
Oh.
One of the we did actually briefly think about that as we were approaching this problem, because one of the statements that we were making this claim that Ron Burt's whole argument was kind of flawed, and somebody came back and said, oh well, all he ever said is that you have higher potential for success if you have these features, right? And so if you're just actually trying to regress on it and success is a rare event, then you might have this problem. And so we did actually think about this classifier thing. But again, we kind of erred on the side of let's small steps towards the goal of like
But now you have the data, so it might
That's right. Yeah, absolutely. So the next thing that I'm going to talk about is kind of the relationship between social networks and successive groups that I alluded to at the beginning of the talk. And so this is work that I did with folks in my PhD program, Andy Jones and Rob Goldstone. And maybe a couple of you, if you saw me talk before, have seen this bit again, but hopefully not, and hopefully you'll get something more out of it if you have. So specifically what we're looking at here is how distribution of knowledge within a group and how that knowledge is shared affects the success of the group as a whole. So it's trivial to say people share good ideas. That's definitely true. This includes skills, techniques, solutions, whatever. It is also true that this communication is situated in a social network, or at the very least in some sort of communication network, be it the work hierarchy or the social network or what have you, but there's definitely some constraints on the way that the information flows, and therefore, QED, people, these good ideas spread through social networks. So given that that is true, you can ask the question, well, what kinds of networks are best for spreading good ideas? And when you say that, does the network interact with the problem space, and if so, how? So this is the question that we were trying to address. And what we did is this was an experimental in the lab. We brought a bunch of people to a computer lab, sat them in front of a bunch of computers, and had them play this extremely boring game where they basically had to guess a number between 0 and 100. They'd get a score that was based on some fitness function plus some stochastic noise. And then they'd also see the guesses and scores of their neighbors in a social network that we placed them in. Okay? And all that we did is tell them to try to get the highest score. So, okay, I don't know what happened there. So basically, well, this is what they saw. Okay, so they had to guess a number in between 0 and 100, and then on the previous round, they'd see this is what you guessed, this is the score you got, and those are the guesses and scores of your neighbors, right? So you might see this thing, okay, if you're this user, you might say, oh, 39, I want to go to 39. That's where the highest score is, so the next round I'm going to also guess 39, or maybe I'll guess 37 or 38, but I'm basically going to go there, okay? And so there's this underlying fitness function, and so you guessed here, and the other people guessed here, and so here's 39, right? You guessed 39. The fitness function will now give you a score, around 42. But what actually you're missing is that there's over here around 70. There's a better point where you would actually get a higher score. So their only goal is to get as high a score as possible. They have 15 rounds to do it, and after each round, they see the guesses and scores of their neighbors. Okay?
Highest cumulative score, highest score on the 15th guess.
Cumulative score.
So, for example, experimenting around the 70 space would be actually penalized. Or might be.
Because there's a penalty for exploration, is what you're saying.
I don't know whether the curve goes straight down or whether it bumps up there. So there was excellent reason for me not to find out.
We actually, yes, that's true. That's absolutely true. There's definitely this trade-off between exploration and exploitation. But certainly, if you are on round 3, in the earlier rounds, there's less of a penalty for exploration, essentially. Right? And so we had variable group sizes. It was very difficult. Actually, it was essentially impossible to control group sizes because you would recruit a bunch of people to come to an experiment, and some of them would show up, right? And so our group sizes were variable, but we built social networks, communication networks for them to be playing in based on a couple of different kind of systematic things. So we had a regular lattice where we would put them in a ring, and we tried to, we put them in a ring. We had small world where it was basically the same as the lattice, except some of them were randomly rewired.
Were they time constrained or round constrained? Both.
They had 20 seconds per round, and then there were 15 rounds.
I see.
And maybe the first round they actually needed the 20 seconds, but pretty much every other time they were like, oh.
How big? I'm just wondering like how quickly they could scan for the max, for instance. Like how many?
So we did a little bit of pilot testing to figure out like kind of, we wanted to make the search space big enough that it wasn't going to be too easy, but also not impossible for them to search, right? And we had to do that while factoring in the fact that they were going to be getting information from other people. So it was, and we did a little bit of pilot testing, not a whole lot, and maybe not even as comprehensive as I would have liked in hindsight, but enough to kind of get it roughly in the area of the right level of difficulty. So we had the small world, which is basically the lattice with some of them rewired, and then we had the random. And for these three, we used techniques that ensured that the average degree was always the same, which was around 3. Okay. And then we had the fully connected one, which was kind of like an upper bound. So this is the case where everybody's got full information. Rather than just seeing 3 of their friends there that see this big long list, depending on how big the group was, right? So they had essentially full information in the fully connected network. And so in our first experiment, we had 9 groups, 7 to 18 participants. Average median size was 10. We had 2 different problem spaces. So the unimodal is trivial. It's hill climbing. It's just you search around the peak and you're there, right? The second one was multimodal, which is kind of the first one that I showed you, where you actually have local maxima, and so you can actually get fooled into going to one of these local maximums. So we had 2 metrics that we were looking at in terms of success. So we're interested in group success. And so the first metric was how many rounds on average did it take for a person to find this global maximum, okay, or this global maximum. And then our second measure of success was number of points per round, average number of points per round, which also yeah, that's right. Okay. So for speed of discovery, this is with the unimodal. Okay, so very trivial, completely unsurprising. In the fully connected network, it took them only 3 rounds, whereas on the others it was closer to 4. The random actually was a little bit in the middle, but basically this is I don't have the error bars on here for whatever reason, but I promise full is significantly faster than the rest.
When you say find it, you mean within
within a half standard deviation, because these are constructed based on a combination of Gaussians, and then we just took half standard deviation and said if they guessed within that. Okay. Yep. So then when you look over rounds, you see the same kind of pattern where, so the fully connected is this one, and you see that they're finding the maximum, much faster. This is the percentage of people that are guessing within this half standard deviation, right? This is actually, if I had put up the plot of the total number of points accrued, it would look almost identical to this. And so, you see this, right, so the fully connected does it really well. All of them eventually converge on it, except for the lattice, which is the ring. In the lattice, information takes a long time to get around, so if one person finds the peak and other people haven't, right, and they're relying on the information from somebody else, it's going to take longer to get them in the lattice. That's one of the things that we specifically designed it for, was to have this long path length.
Everyone, therefore, does not have a constant. Well, rephrase. Does everyone have a constant number of neighbors?
No. We did in the lattice random and small world, we controlled for the average number of neighbors, so it was always around 3, but there was variation between people. And certainly there was like everybody had the same degree in the fully connected. Yeah. So here's one of the most interesting results in my opinion. This is the multimodal, okay, and this is how quickly they found it. And what you see is actually the small world network on average found it faster, found the global maximum faster than the fully connected where they had complete information. Okay, and we're still seeing the lattice being the slowest. Okay, and when you look at the convergence, what you see is that it's almost as though you would expect this to be the fully connected, but I promise it's the small world. They get an early start and end up, everybody ends up converging, even the lattice, but the small world gets this kind of early lead. And we don't know exactly why, but based on we actually kind of looked at the exact patterns of where people were guessing in some of these, and we kind of developed a hypothesis for why this was happening, which is what we'd see with the fully connected is kind of the situation that I alluded to at the beginning of this, which is people would, you'd see this long list, and it just so happened that nobody had guessed in this particular range, and somebody had guessed in this particular range, right? And so they'd all quickly converge, like within the second round, they'd all converge, and about 2/3 of the time, they'd have converged to one of the local maxima rather than the global maximum. And as a result,
So something you might find interesting is I recently saw another study, and it seems like in cases like this where there is an unknown fitness function, people have this very strong unimodal assumption, and there's like a reward payout from a slot machine where it's bimodal. People just do completely the wrong thing because they'll hit once in the valley and they'll be like, no way, and I'll just stick to this one mode that I know. So it may be some of that tying into your, it's interesting.
I'll talk to you about that.
When I look at the lattice curve, it does march constantly upwards.
Yeah.
So, boredom?
That is, yeah.
What I would expect from what you told me is that it would start low and would near zero, and it would stay low near zero because no one would be near the global maximum. They'd all be near some local maximum.
Oh, right. So yeah, and absolutely boredom is the exact right answer. Basically what you would see is that if I plotted this for a single run, like these are averages, right? So if I plotted it for a single run, a lot of the times what you'd see is, right, exactly, you'd see kind of like flat, and then like some jump up around like round 7 or so, because basically people found a local maximum in the first 2 rounds. They stuck there for a while and then they got bored, right? But boredom and exploration, kind of the same thing, right? So we thought this was really interesting. I mean, we really expected the fully connected network to be the upper bound, right? It's complete information. We really expected it to be the upper bound. And what we actually found was that the small world was doing better.
Supposing you had no time constraints, do you think you'd have had a different answer?
Well, I mean, what we're seeing is this difference being in the very early rounds, right? So regardless of how much, I think in the end, just by everybody's gotten there and they're staying there, eventually this little difference would get washed out. But the difference that we're seeing is in the early rounds, so it doesn't matter how much time we give them.
But again, I mean, I think it's not so surprising because they're not seeing the plots on a graph, right?
No, right. They're just seeing these boring lists of numbers.
So I think if you imagine a human having the mental model of a unimodal distribution, they scan the list, they look for the max, they're like, it's got to be close to the max.
Yeah, absolutely.
And that's why
I completely agree. I think that's a really good explanation, and actually would, like I say, would love to see that paper because I think that would be fantastic for this. We did another one. Basically, this is the same setup, same social networks that we were manipulating, and a different fitness function. And we call this the needle for obvious reasons, right? And so this is actually, again, specifically meant to design to fool them in this exact way, right? They see this, what looks like a unimodal distribution, and finding this, in order to do this, they have to do some real exploration in this very low, no-scoring problem space. And in fact, the range in which they can get any points at all greater than 0, essentially. I mean, there's stochastic noise, right? But is about a 5-point range. Right, and I forgot to mention, we did change where these were located. It wasn't always at the same points. We counterbalanced it and so forth and so on. But, and so what we found in this case was actually looking at how quickly, on average, people converge to it was not a very informative measure because it turns out that almost all the time nobody found it. Okay, and so then you have the censoring at there are 15 rounds, that's as long as they had. So this is a situation where we might have actually seen some differences if we had given them more time. But trust me, they really didn't want to be there any longer than they had to. And so instead what we do is we look at how many groups found the needle at all. had somebody that found the needle that actually made a guess within here. And of course, when somebody had made a guess within here, they always stayed there. They immediately realized that it was better than over here. But and so in this case, the number of groups, when we're looking at the number of groups that found it, it was actually the lattice that did the best, right? So, and in fact, when you look at the convergence, so this is, so this is the global maximum. This is actually how many we're guessing, the percentage that we're guessing within the range of the needle. And this is how many people we're guessing within the range of the local maximum, right? And what you see is basically, oh right, so here you see this squares, they're going to the local maximum, this is the lattice, they're going to the local maximum at first, but slowly they're starting to go away from the local maximum and starting to go towards the needle. And this is of course on average. We have to take it across all of the groups and whatever. And so the idea is that basically what we're seeing is that the lattice, as I mentioned, the thing that was causing a problem in the unimodal, where it was taking a long time for this information to travel around the social network, is actually benefiting them here because people are doing more exploration. They are less likely to have seen somebody that has guessed within the local maximum, which means they're going to continue doing exploration, which means they're going to be more likely to find the needle. And once they've found it, that good information can then propagate to the rest of the people in the network. And so what we're seeing here is this very clear trade-off between exploration and exploitation. And in fact, what we see is that these different networks, based on the speed of transmission of information within them, actually encourages exploration over exploitation or vice versa. And importantly, which is going to be most beneficial for the group is going to depend on the kind of problem that they're looking at, right? So if it's a unimodal case, you really want fast transmission of information, because that'll get people, as soon as somebody's found it, they'll all converge to the correct solution because there is only one correct solution, right? But if you have something more like the needle, where maybe there's a really good solution that's not easily found and requires a lot of effort, maybe you actually want to slow down communication between people so that people are doing more exploration. There's work on brainstorming that shows that people are a lot better when people brainstorm independently and then you put the ideas together, because even just as an aspect of turn taking or whatever, when you have this kind of very rapid communication, it actually diminishes people's creative ideas. And so if you have people, this is analogous to slowing down the communication. And so, yeah.
If I can slow you down. Did anybody try like uniform intervals, just sampling on uniform?
Yes. It was not a very successful strategy. Yeah, basically, if you had infinite time, of course, that would be reasonable. So what I'm about to talk about, just very briefly, because I'm essentially out of time, is kind of where I want to go next, right? Which is, I want to actually combine these two things and look at how the social network structure affects both individual success differentially and group success differentially, okay, simultaneously. And so what I'm doing, oops, oh, right, this is my, yeah, okay, so from the two studies we know that, okay, position of the network affects individual success and overall structure affects group success, right? So what I want to do is combine them. And so what I'm thinking of doing is, and actually I've started building this and I'm going to be running it in the next month, basically. So now we've got it's essentially the same kind of setup as I had in the experiment that I was just telling you about. Except in this case, instead of being a one-dimensional, they're just guessing a number, they're actually going to be searching a field with a problem space. So another nice thing about this is that there's noise here, right? So there's, where you guess, it's not a smooth landscape, but it's not stochastic noise. Okay, so there's a definite answer. If you guess here and somebody else guesses here at the same time, they'll get the exact same points as you, right? Right. So there's no stochastic noise. It's a little bit more fun because you're clicking. I'll actually show a demo of this in a moment. So this is just the setup. But what's interesting to me is to take these kinds of graphs, okay, where in this one, basically you're maximizing, I actually built a little genetic algorithm to design these so that I'm maximizing the variance of the betweenness, Okay? So the person here is going to be very, very central, and the people here are going to be very, very non-central. Okay? So within this group, and what's nice about this is that every single, this is, I've fixed this is fixed degree, so everybody actually has a degree of 3. And so they're all getting the exact same amount of information. And so if we see differences here compared to here, then we'll actually have experimental evidence that these positions really matter as a result of betweenness versus not, right? This one maximizes the average closeness. Okay, and there's another one that I didn't put up that maximizes the variance of the variability between closeness. So we can look at within a single network, how does a very close individual, how do these particular structural properties affect the way that these individuals succeed? I also want to look at, using this methodology, how groups specialize. So this is what I wanted to get at your question, Chandra, is what I'm interested in is, a real ideal strategy. If you're working with the same group over time, the ideal strategy is to initially distribute yourselves uniformly, right? But if all you have to go on is essentially the only thing that you see are the people that you're connected to, you might be searching the same place as somebody that's 2 or 3 hops away and not know it, right? So that information has to propagate. But it's possible for that to propagate, right? I mean, you look at the graph coloring experiments that Sid Surrey and Mike Kearns did, and here you only have local information, but as a whole, the graph is able to attain this kind of coordinated state, right? And so I think that you might be able to see the same sort of thing if people are iterating on this and working with the same people over time. Maybe at round 0 of the 6th trial of this, they're going to have learned to optimally distribute themselves in the space. So that's something that I also want to work on. And so, yes, brilliant. Okay, so this is essentially how it's going to look. They're going to see feedback in terms of how this is what the other people guessed. And so you can, where's the mouse? Here. So you can see that this person, the little yellow marker that's getting highlighted right there, that's what person A did, and this is the score that they got. These are your guesses in previous rounds, okay? And you can see the score that you got, and it's of course color coded in the same way. One of the things in the previous experiment that I felt I was like, I really wish I could have fixed this, is that we could kind of look at copying by saying, oh, this person guessed near where this other neighbor of theirs guessed. But you can't really differentiate between that and exploration, right? I mean, and just like them guessing the number because they wanted to guess the number rather than because they saw it from somebody else, right? There's no clear thing. Here, we'll give people the option to actually explicitly copy, either their past behavior or their neighbor's behavior. Right? And so the little problem space that I had showed you before is actually going to be embedded in this map. They're not going to see anything. We'll frame it as an oil exploration thing. And so they'll actually get to play this game. Hopefully it'll be more fun than just guessing numbers, and so we'll actually do it. And here's the plug for HComp. I'm going to be I'm going to be doing this on Mechanical Turk, recruiting the participants in Mechanical Turk. And so we've actually got this method. We've figured out that you can get maybe 8 people to work simultaneously, right? If you're lucky, right? To get people to show up at the same time and work. But we've got this method to build, basically you can build panels. And by doing this, you can actually get large synchronous groups working together. And so that's actually what is necessary in order to have those networks that I was showing you before. You need to actually be able to get people there participating at the same time. This is the reason why I haven't followed up on it since I left grad school, is because I just didn't have the resources. I didn't know how to get that many people working on a problem simultaneously. And so now we have the method, and now we're going to do it in using Mechanical Turk, and then there's this human computation workshop that everybody should go to where work like that will be presented.
Is the color coding now according to function value, or is it?
Right, so that's the score that they're getting. Right?
I see. So that's interesting, because now compared to the previous one where there was no visual prep of the function as you're exploring it now, because this might introduce, I mean, for better or for worse, right, it introduces some another aspect into what's going on. Because, for instance, there, right, if you had plotted the points on an axis, the multimodality might have become more
obvious. That's right.
Because you'd seen them as opposed to being a list. Whereas here, you will see that instantly, the visual aspect, which I expect will help people.
Yeah.
Yeah, in fact, it makes me wonder about things like will the color linger between rounds so that we're gradually filling in a map? Or
yeah, that's something that I'm not sure whether to be worried about it or not, right? Is the fact that I feel like this presentation might encourage exploration independent, just by virtue of this presentation.
Color the map, yeah.
Right, exactly.
It's a good question.
Yeah.
It might be interesting to look at the behavioral difference between this and something that's more like a list.
Yeah.
It'd be very hard for people to deal with this for this
Yeah.
piece of data.
two-dimensional
Absolutely.
lists as well.
My hope is that I mean, so the way that we're going to do it is we're going to actually pay people based on their points, right? So and we're going to allow people to play this repeatedly, right?
Oh, the other thing you could do is you could kind of you could make a false limited memory where you only kept the last.
Yeah, absolutely.
points.
Yeah.
So that would reduce the coloring instinct. You just.
Yeah, actually, I mean, that's a very good idea. That's actually something that I had thought about earlier, and I've kind of, I mean, because I was thinking about that because I was also thinking, do I also want to show the history of the other players, right? Right now, all I'm doing is showing your own personal history, right? Rather than the history of both you and all of your neighbors. So you're not actually coloring out the whole map. You're just seeing kind of your personal history.
Oh, I see. That you're saying your neighbors ones too.
No, right. But that's a relatively arbitrary decision that I've made, And the hope is that these, features, yeah, they're definitely going to affect the way that people behave, but the hope is that we'll still see the differences in the networks and the network positions, regardless of whether, of which particular one that we choose. So long as we're constant across the different networks, and the different positions within the networks, hopefully we'll see the difference regardless of what kind of information presentation we choose. I mean, it is possible that maybe if I select one particular presentation, not showing the history, whatever, that the differences will be greater or less than some, but hopefully we'll see them regardless.
The fear I would have would be in the particular case of not showing your neighbor's history, because I kind of assumed that that's what you were saying, like your clicks as well as other people's, that people might just not realize that there's anything other than what they've put in. So you might chop off the network effect.
Oh, I see what you're saying.
So this one might. I mean, you're right that it would still affect it uniformly, but this might be a really big effect.
That's true. That's a good point. And actually, yeah, I mean, I'm still looking for feedback on this presentation, so this is actually very useful because, like I said, I haven't launched this yet, so there's still room to play. Okay. Any questions? Okay. Thank you.